Hello everyone, myself Atharva Deshmukh. I am from ADC Asta in second year aeronautical branch. My topic is general lift distribution in the low speed aerodynamics subject. I have the topic IC2 for the video presentation. As a part of introduction, the general lift distribution in a finite wing refers to the variation of the lift across the span of the aircraft wing. Unlike infinite wing and finite wing experience a non-uniform lift due to the factor like wing geometry and aerofoil shape. Typically, finite wings are generated more lift near to the root and less towards the tip, achieving an optimal lift distribution is crucial for the efficient and stable flight. Computational methods of the wing tunnel testing help for the analyze and design the wing with the desired lift characteristics. For the perfect understanding of what is a general lift distribution, we know that what is meant by the downwash and what is their effects. So for the understanding the downwash, we have this figure. This figure is an aerofoil structure. This is the leading edge and this is the trailing edge. This is the chord length. This is the alpha effective. This is alpha induced, and the total angle of attack from the horizontal is alpha. We know that alpha equal to alpha induced plus alpha effective for the aerofoil section. This is the induced drag, this is left, and this is alpha induced in the vertical direction. As we know the previous, the Prandal's classical lifting theory are the very important for the finding the general lift distribution from the apart topics. The Prandtl classical lifting line theory analyzes the lift distribution of a finite wing representing the all lines in the vertices is provided in the Prandtl region as follows. This is the streamline velocity, this is the airfoil structure, this is Z, Y and X direction, that is the lift in the Z vertical direction and drag in the opposite in the direction of twisting velocity. It is the span of minus b by 2 till b by 2. This is the vertex sheet delta equal to tau naught y dy x and the y and z direction. Now the further explanation in the next slides. It is a bad-shaped formula. Infinitesimal contribution for the velocity induces along the lifting line at the point in bracket 0, y naught till y. It is the del w. It is a downwash with the derivative. The dw equal to minus tau y dy upon 4 pi y naught minus y. The total velocity induced at the point is obtained by the integrating. We know that the integration of the derivative, it is the main function y naught in terms of downwash w y naught equal to minus 1 by 4 pi integral of minus b by 2 to plus b by 2 tau y naught dy divided by y naught minus y. Due to the general non-uniform distribution, the induced velocity along the wingspan and the effective angle of attack has individual value of the each wing. We know for the downwash and the previous effect of downwash on the local flow over the local airfoil section of a finite wing, the alpha is the angle alpha equal to alpha effective plus alpha induced. For the small angles, alpha induced y naught is nearly equal to minus w by y naught divided by free stream velocity v infinity equal to 1 by 4 pi v infinity into the integral of minus b by 2 to plus b by 2 tau dash y dy upon y naught minus y. Clearly, we the previously known the effective angle E alpha effective equal to alpha effective of y naught in the direction of y. For the small angles, can assume the local lift of coefficient changes linearly with the angles. Hence, the coefficient of lift means the coefficient of force of the lift CL of y naught equal to n infinity divided by alpha effective in terms of y naught minus alpha naught y naught. Here the a naught denotes the slope of the lift characteristics for the wing section. A naught it is the angle of attack corresponding to the zero lift. Note the alpha infinity or A infinity equal to 2 pi if the thin aerofoil theory is used. Note that in the general the angle alpha naught equal to alpha naught y naught. So the by the Kutta-Joukowski's formula L dash y naught equal to 1 by 2 rho infinity v infinity square CL of y naught into cy naught equal to v infinity tau y naught, where the c y naught is a local chord of the wing section. Means it is a local chord of the wing we are taking. Hence, the local lift of coefficient equal to CL of y naught in equal to 2 tau y naught divided by v infinity c y naught. Assuming that a infinity is equal to 2 pi in the previous formula, the local effective angle of attack is alpha effective y naught equal to tau y naught divided by pi v infinity c y naught plus alpha naught y naught. Finally, the sum of the two local angles alpha effective y naught and alpha induced y naught is equal to the geometric angle of attack alpha. If the wing has been the geometric twist, the angle of attack also depends on the span-wise location, that is alpha equal to alpha y naught. Hence, we have to obtain the following integral differential equation for the span-wise distribution of the circulation. There is the main derivation and all the formula we are substituting in this. The tau y naught divided by pi v infinity c y naught plus 1 by 4 pi v infinity under root 4 pi v infinity integration of minus b by 2 to plus b by 2 tau y dy upon y naught minus 5 is equal to alpha y naught minus alpha naught y naught. Once the equation is solved, then the span-wise distribution of the circulation is known as the lift force developed on the wing can be calculated as follows. L equal to, means the lift equal to integral of minus b by 2 to plus b by 2 L dash y dy equal to rho infinity v infinity integral of minus b by 2 to plus b by 2 tau y naught tau y divided by dy. The global lift coefficient is CL equal to L divided by Q infinity by S equal to 2 rho to V infinity S integral of minus B by 2 to plus B by 2 tau y dy. The local contribution of a drag force is drag induced equal to L into sin alpha I is nearly equal to sin y due to the very small angle. The induced drag force is equal to di equal to integral of minus b by 2 to plus b by 2 L dash y alpha I y dy equal to rho infinity v infinity integral of minus b by 2 to plus b by 2 tau y alpha I y divided dy. Here the alpha is an induced angle. From the previous slide, we can continue from this side. The coefficient of induced drag is equal to CDI equal to di means induced drag divided by q infinity into s equal to 2 divided by v infinity s into the integration of minus b by 2 tau y naught alpha induced y into dy. The important case in the elliptical distribution for the circulation, assume tau y equal to tau naught under root of 1 minus 2y by b bracket square. The lift dash equal L dash equal to y equal to rho infinity v infinity tau naught under root of 1 minus 2b 2y divided by b bracket square. After the squaring this bracket and the multiplying this, the tau dot y means the tau dash y equal to 4 tau naught divided by b square into y upon under root of 1 minus 4 y square by b square. It is the squaring of this bracket, we get this. Hence the d hence the wy naught equal to minus of 1 by 4 pi cyclic or limiting integral of minus b by 2 to b by 2 tau dash y dy upon y naught minus 5 is equal to tau naught by pi b square integral of minus b by 2 to plus b by 2 into the y dy and divided by the y naught minus y in the root of 1 minus 4y divided by b square. This is came from this. This is the whole table are taken from this. Now, this is the overall basics that we know for the general lift distribution for the understanding properly. The all formulas of the previous, the elliptical lift distribution, as well as the Prandal line theory, it is very important for the understanding of the general lift distribution. So apart from that, the general lift distribution refers to the variation of the lift across the span of a finite wing. Unlike the finite wing are experiencing non-uniform lift due to the factor of such as wing geometry, airfoil shape, and the aerodynamic effects. The typically the lift distributed is a higher near to the root and the decrease towards the wing strip wingtip. Achieving and the optimal lift distribution is essential for the efficient and the stable flight. The computational method and the wind tunnel testing are employed to analyze the wings with desired lift characteristics. Now we are going further for the derivation part of the general lift distribution, that we are including the general lift distribution and industrial drag and coefficient of lift. Again, we use the transformation of y equal to minus b by 2 cos theta and theta in between 0 to pi, and the elliptical distribution is expressed now as tau theta equal to tau naught under root 1 minus cos square theta equal to tau naught sin theta. Generalizedly, it shows tau theta naught equal to 2v infinity b, the summation of n equal to 1 till the infinity a n sin n theta. We need to derive del tau by dy equal to del tau by d theta into d theta by del y. We know that the derivative of d theta and d theta will get cancelled, and again it formed by d tau by dy. But for the derivation, we are split it into the two. Then the d tau by d theta into d theta by d tau further equal to the 2v infinity b d theta by dy, the summation n equal to 1 till infinity n a n cos n theta. For the central equation of the lifting line theory takes a form alpha naught minus alpha naught theta naught. Again I will revise the alpha theta naught minus alpha naught theta naught equal to 2b alpha c theta naught summation of n equal to 1 till infinity a n sin n theta plus 1 by pi summation of n equal to 1 to infinity in bracket n a n integral of 0 to pi cos n theta divided by cos theta minus cos theta naught d theta. There are many terms n in the series can be taken as the desired for the accuracy. The coefficient of an where n equal to 1 till the n in the equation are known. However, they must satisfy the fundamental equation of the Prandal lifting line theory. That is, an must satisfy the equation. Differentiating the equation, we obtain d tau by dy. After that, in the previous slide, d tau by d theta and d theta by dy we calculated. From that, we are getting the alpha naught equal to 2b pi c theta naught, the summation of 1 till n a n sin n theta plus alpha l equal to 0. What is meant by alpha l equal to 0? That we are getting. This is meant by at a lift equal to 0, what is the alpha means what is the angle here are the shown. It is known as it is evaluated at the given span-wise location. Hence, the theta naught is specified in terms of b, comma c theta naught and alpha l equal to 0 theta naught are known as the quantitative form of the geometry and the airfoil section of the finite wing. The only unknown in the equation are an. Hence, the written equation given as span-wise location. It is an algebraic equation with the n unknown. However, let us choose n different span-wise station and let the evaluate the equation as each of the n station can we get obtain the system of n dependent. So we know that nm equal to 0 to pi, comma n equal to 1 to l. This is a way to the linear algebraic system is obtained from the unknown coefficient a1, a2 till the an, which can be solved example was Gauss elimination method. By the previous, the algebraic equation of n unknowns, namely a1, a2 till the an. Now the tau theta naught is known by the equation. The lift coefficient for the finite wing follows immediately from the substituting the equation. CL equal to 2 V infinity. V infinity is the free stream velocity into S integral of minus b by 2 to plus b by 2 tau y dy equal to 2b square by y in summation of n equal to 1 till n an integration of 0 to pi sin theta d theta. What is meant by sin n theta d theta? We know the previous the an and we eliminated by the cos elimination. Now the equation become 0 to pi sine n theta sine theta d theta in the limit of pi by 2, then n equal to 1 0, then n not equal to 1. Then we obtain the formula of Cl equal to a1 pi b square by h equal to a1 pi r. This is the radius r. It is shown the symbolically like this r. We see that only the first coefficient of Fourier series is needed to calculate the lift coefficient. So due to only this, we can calculate the coefficient of the lift and the lift force coefficient. Note that the CL depends on the only the leading coefficient of the Fourier series. The induced drag coefficient is obtained from the substitution of the equation into the equation as follows. The coefficient of induced drag equal to 2v infinity s integral of minus b by 2 to plus b by 2 tau y alpha I. Alpha is induced angle y dy equal to 2b square by s integral of 0 to pi alpha I theta sin theta in bracket the summation of n equal to 1 till n an sin n theta by d theta. This is the Fourier series that we know. From that the calculation we find the induced alpha equal to 1 by 4 pi v infinity integral of minus b by 2 to plus b by 2 tau dash y dy upon y naught minus 5 equal to 1 by pi summation of n equal to 1 an in the bracket 0 to pi cos n theta divided by cos theta minus cos theta naught d theta equal to the summation of n equal to 1 till n an sin n theta naught divided by sin theta naught. Hence the formula for CD induced being transferred as follows. Coefficient drag induced equal to 2b square by s integral of 0 to pi sin theta summation of k equal to 1 by n k a k sin k theta by theta and another bracket is 1 summation of n equal to 1 till n sin n theta by d theta. After the solving this 2b square divided by s into the summation of n k comma n equal to 1 k a k a n integration of 0 to pi sin k theta sin n theta d theta. It is the expansion of the Fourier series and the calculating or the things. Again, the using the orthogonality property of the Fourier series, integration of 0 to pi sin k theta sin n theta d theta for the value 0, k is not equal to m and 1 by 2 pi is k equal to m. From the formula, the induced drag coefficient simplifies the form. The coefficient of drag di equal to 2b square s into pi by 2 into the summation of n equal to 1 till n an square equal to the a r summation of n equal to 1 n a square equal to pi r in bracket a1 square plus summation of n equal to 2 till n an square is equal to the pi r a square in bracket 1 plus summation of n equal to 2 till n into an square divided by a1 square. Can we write the shortly CDI means the coefficient of induced equal to CL square divided by pi r in bracket 1 by del is probably known as the CL square divided by pi r e, where the del equal to the summation of n equal to 2 till n into an square divided by a1 square. Note that del not greater than equal to 0, hence the coefficient drag induced in the elliptical wing is lesser than or equal to coefficient drag in any wing optionally. This is the total explanation about the general wing theory and their basic from the Prandal lines theory. Thank you.